Example 4, a box with square base and open top must have a volume of 32,000 cubic centimeter. Find the dimension of the box that minimizes the amount of material used. Again, this is from section 4.7 and this is the part 4. And so let's see, we're discussing a box with an open top. Like this, and it has a square base. So here and here they have the same dimension, and then you have another dimension over here. And we're trying to minimize the amount of material. So objective is to minimize the surface area, basically. A equal to 4 walls, 4x times y, plus a base, x squared. And then constraint is that the volume, which is x times y, has to be 32,000 cubic centimeter. Now, from the constraint, you solve for y. And then you plug it back in. And a of x is going to be 4 times x times that, which is going to be 128,000 over x plus x squared. Then take the derivative. And derivative is going to be negative 128,000 divided by x squared plus 2x. And notice that x is not part of the domain right there. 0 is not part of the domain. X in the denominator and was also in the not in the domain right there, sorry. And so to find the critical points, critical values of a, we want to set a prime equal to 0. To do that, I have to simplify. And common denominator. And plus 2x to the power 3 over x squared. Now, setting 2x, and then I can factor 2 out on the top, and I get x to the third minus 64,000 equal to 0. This is going to give me x equal to 40. So x equal to 40 is a critical number. We can plug it back in to solve for y, and that would be 20. So y equal to 32,000 divided by 40 to the power 2, and this is going to give us 20. So that's the dimension if the critical number gives us the minimum value. And so how do I figure out if this is a minimum value? Domain is not very nice. Domain is not closed and bounded. X can basically get as small as possible and get as big as possible, making y smaller. And so domain is domain is 0 and infinity, and I have to use the second derivative test because third derivative test is just more work for me, I think. Well, sometimes it can be good. You can second derivative test is a good option too, because taking derivative here is not too bad. But let's try to do first derivative test first and see how it goes. First of all, you only had one critical number, and that helps. If you, within the domain you only have one critical number, then however you go, you it's possible to say that the local min or local max is going to be the absolute min or absolute max. If you had more than one critical number within the domain, then local min and local max may not be the absolute min and max. And that's the trick that we use for the second derivative and first derivative test. And by having one critical number within the domain. Okay, so in here, if I put in 20 in here, 0, and then where is the derivative? The derivative is right here. So for values less than 20, we're gonna, in values that are smaller than 20, we're gonna get basically a negative value out of this. For values that are bigger than 20, we get a positive value. So decreasing, increasing, local min is at 20. So the solution to the question is 40 times 40 times 20. And you can plug that back into here to see what how much what is the amount of surface area that you will need.